almost on time. Okay, much to cover. So let's start. And with in case someone's late, the first 5 minutes are basically repetition. At least the problem I introduced yesterday. After introducing what approximation algorithms are and seeing a first example on the vertex cover problem, we'll start seeing a few more interesting techniques to design such algorithms. And we'll do so mostly for now on the set cover problem, which is formally defined here. So it's we're given a universe. We'll assume here that there's n things in the universe. It's often convenient to take the first n integers, but that's will not be too strict about that. And then the input consists mainly of sets, subsets of this universe, so a collection of sets from elements in the universe. And in the general version, these sets have certain costs that we can specify. Then solutions are such that collections of subsets, or here formally the output is a collection of indices, so that if I take all the elements with indices in that set curly C, then I get as the union all of the universe back. So I have to cover the whole universe by making a selection from the sets I'm given. And the cost of such a selection is just the sum of all the sets costs, and that we want to minimize. Clearly we would want for an input to make sense that at least if I take all of the k sets that they cover U, so otherwise the problem is not feasible, then certainly we want to minimize because I can always take all sets. And we assume the costs are weakly positive, say. There's a restricted version. You can either call it the cardinality version or the unweighted set cover version, where I guess the number, that's a weird version. The cost should be 1 for each set. We just count how many sets we take. I think I was jumping ahead of myself here. Unweighted set cover is a strict generalization of vertex cover, where we have the additional property. So as I mentioned yesterday, if you have some graph, let's maybe draw a short example. One way to think about the problem could be this. So a vertex cover has to cover all the edges. So the edges become these elements in the universe. And any specific vertex that I pick covers a certain subset of the edges, namely its neighborhood, or all the, I should say, the edges incident at that vertex. So if you have a vertex cover instance, it is a set cover instance, but it's a special set cover instance, namely every edge occurs in exactly the sets of its 2 endpoints. So it's not a completely general set cover instance, but one where every element of the universe occurs in exactly 2 sets. And we normally think of vertex cover as being unweighted, so we just count how many vertices we have to pick. But of course, you could define a weighted version of vertex cover. If you want to have a generalization that stays in the realm of graphs, you could say we were going to hypergraphs. In a hypergraph, edges become hyperedges, so just any subsets of vertices. And then clearly you can always map an instance of set cover into a hypergraph where you have the vertices for the elements of the universe, 1, 2, 3, 4, 5, 6. And then you can draw, say we have a set that contains 1, 3, and 4. So that could be SI 1, 3, 4. And you just draw a hyperedge around those. And if you have a bunch of those hyperedges, maybe there's a few ordinary edges as well, and then you have a few of those, then you can ask what's the smallest number of them that I have to pick to cover all the vertices. This smallest. I guess these are the hyperedges. So am I confusing the picture now? Yeah. Each of these sets corresponds to some vertex that's contained in all of those. So I didn't draw the vertices. I should have drawn this differently. The hyperedges become the vertices. Is there a nice way to draw this directly from the sets? Okay, you know what? Let's leave it. I don't know if I can put it in a nicer picture next time. Either way, it's a generalization of vertex cover, and you can formally define it as a hypergraph, but it's not helpful by much. We're mostly using this as to illustrate things, but we'll also see that set cover can represent some other problems in terms of reduction. If you think about optimization problems and approximate solutions for them, a natural approach is to try some simple myopic greedy heuristic, which you should usually get some feasible solution from, but oftentimes you don't get a guarantee how good it is. And so it's a natural approach to say, let's start with a somewhat simple greedy algorithm and see if it is an approximation algorithm. And so we can do that for set cover as well. The natural notion of greedy here, for the fully general problem, if you want to take cost into account, I guess if you think about it for a moment, is that you want the best set in terms of cost per new element. You may have some collection of sets already, and then there's all the sets that you haven't picked yet, where you can choose which one to pick next. But some sets are more valuable than others because they give you a lot of new elements that you haven't covered yet and that you will eventually have to cover. And they do this at different costs. So it's not so useful to take an expensive set that only gives you a single new element if you could, for the same cost, cover several. I think that's the intuition. The intuition behind that is quite clear. You want the cost for each element that you cover to be small, because you have to cover the same number n in total in any solution. So a formal way to greedily pick always the next best set in terms of the cost per new item ratio is spelled out here. We start with having nothing covered. C is the elements that we have already covered, and curly C is the indices of the sets that we used for that. So at the end, the curly C is the actual solution, but we need to keep track of how many elements we still have to cover. So as long as we haven't covered everything, we find a set that minimizes this ratio, the cost of the set divided by how many elements does this add to the covered elements. So the sets as I subtracted all the elements that we have already covered with other sets. And we find the one that minimizes this. That's the one we pick next. It's a greedy algorithm. We never take a step back. And we keep doing this until we've covered all elements. Here again, I'm assuming the instance is feasible, right? Otherwise, this while loop might never terminate. I think always in the following, we'll make this assumption that if I take everything, then I get the universe back. There's a few annotations there that are kind of not part of the algorithm, but are useful for the analysis. The while loop is not a for loop with specific iterations, but of course you can speak about the ith iteration, just the way it's run. And we keep track of the price at which we covered certain elements. So alpha I is the cost per new item ratio of the set that we picked in the ith iteration. And for all the elements that we now gained in the covered elements C, for those elements we set the price at which we have covered them to alpha I. And so you can, immediate observation is that this price over time and the alpha i's can only increase because we're taking away elements that could have reduced the cost, and we're always picking the best current one. Now, the key lemma to understand how well this algorithm works is this price lemma that tells us something about, say, the worst case of these prices for specific elements. And for that, we rename the elements in the universe so that they appear in the order that they're included here in the set C of covered elements. So this is what this order is referring to. And then it says the elements indeed become more costly over time. At least we have an upper bound for how much we have to pay to add this element to our set of covered elements. And it says in this algorithm, it's upper bounded by the cost of the optimal solution. But here this opt refers to the entire set covered. And it's divided by some term that when I gets bigger becomes smaller. So the overall upper bound here gets worse. Let's prove this. It's a simple proof, but I think it's insightful to do it briefly. Consider the time when we cover this jth element. Now, we usually cover those in batches of including an entire set, essentially in one time step gives you several elements, but we logically separate that into covering one element after the other. So before this element is included, we've had obviously j-1 elements covered because that is the jth one. So there were n-j-1 elements left uncovered. We'll use this complement set going forward. Now, if you take any optimal set cover, curly C star, that one, even if I'm partway through my algorithm, I could always say, okay, I've made some initial decisions into my curly C, but for now, I'm just going to keep it as it is and add the optimal solution on top. Certainly, the optimal solution has to cover these remaining uncovered elements because it covers everything, and it does so at cost at most opt. It seems like a very crude argument, but we'll see it's essentially tight. So it means that there must be some set, and indeed it could be our set that we here pick in the minimization, which is, I guess, in the optimal solution, but not yet picked in our solution, where you can bound this this cost per new item ratio, and we can upper bound this by the cost of the optimal solution divided by the elements that are left to cover, because assume towards the contradiction this wasn't the case. There was no such set left with such a low cost per new item ratio. Well, then if you take this average cost per element and sum it over all the remaining elements, it means that you would need strictly more than opt divided by C bar cost if you sum it up over all those C bar elements, you would require strictly more than opt to cover just the remaining elements, but the optimal solution covers all of them at cost most opt. So that's a contradiction. So we always find a set Si star where the cost per new item ratio is at most opt divided bar C. And then I'm just inserting. So it's a relatively crude argument. We're just saying at any point in time, I could have continued with the full optimal solution, and that gives me a bound of how much I have to pay per element. If you plug this, if you put this together, you get an approximation ratio for the set cover problem. And what we get is an Hn approximation. So Hn is the harmonic number. And you will remember, maybe popped up in this module a few times, that this is, you can write it asymptotically as the natural log of n plus some infamous constant, and then a lower term. That's the Euler-Mascheroni constant, 0.57 something. But the basic message is it's by and large natural log of n. So this is growing with n, right? It's not a constant factor approximation, and it's maybe not so great. But let's first prove it before we dismiss the result. So we want to bound the cost of our solution that the greedy algorithm finds. That's the cost is the sum of all the costs of the sets that we pick. And I can rewrite that as the price at which I included all the elements. That's just here I'm summing over the cost of the sets. Here I'm summing over the elements. Now some elements are covered by multiple sets, but the price is defined such that it only takes the new elements into account. So when I cover some elements several times, right, so here's my universe. Say I'm first covering these elements. The three of them share the cost of this set. If the next set is taking these elements, only those two new elements share the cost of this new set. So it's just rewriting the sum over the cost of all the sets that I pick. And now, of course, we use our price lemma to upper bound the price. That's a simple calculation then. And you pull out up, which is a constant factor, you're left with that sum, and that's exactly the nth harmonic number. So it's a very simple analysis. No fancy math needed here. But I really want to stress again, this was just the simplest greedy algorithm that if for the weighted version of set cover, it's the most natural thing to try. Always pick the element that gives you on an amortized cost per element that you gain the best next step. But really an approximation guarantee that grows with n is not so great. Could be a large factor if the input is big. Unfortunately, this is essentially the best we can hope for again. In the worst case, you can consider, for example, the following instance. It's a star graph. The worst case instance is indeed a vertex cover instance where every element in the universe occurs in at most 2 sets. But I need here a weighted version of vertex cover, and the weights are chosen so that this fails. So I'm putting a weight of 1 plus epsilon here on this center of the star. And then I'm putting harmonically increasing weights on the elements around the star until I have 1. And so what happens in the greedy algorithm is initially this vertex looks, this singleton set that just gives me this one edge. It looks really attractive because it's very cheap. Whereas this other guy here would give me n edges, but at the price of 1 plus epsilon. So the cost per element for the center initially is 1 plus epsilon divided by n, whereas the leaf has 1 over n, so that wins. So I'm going to pick that leaf in the greedy algorithm, and then the same thing happens again. I have 1 less element to cover, so I have 1 plus epsilon divided n minus 1 in the next step. And so again, this leaf appears cheaper to the greedy algorithm. And so it picks all the leaves around there, all the n sets, whereas I could have picked the center at the start. So the optimal cost is 1 plus epsilon, which is obvious here. But the greedy set cover decides to pick all the leaves around there. You can even boost this construction for the unweighted vertex cover problem. That's more tricky, and I don't don't think that's super insightful, but it's a nice puzzle to think about. You can show even if you take the unweighted vertex cover, then the greedy algorithm, as we've shown it, is not going to work well. Of course, you can do better on vertex cover. We've seen the approach with matchings last time. But if you, so this is for greedy. You can show that this specific algorithm is not doing so well. There, this kind of logarithmic growth seems inherent. In the next section, we'll look at some more problem-specific technique for set cover that achieves a different result, I'd say. I think it's usually stronger. Whereas the greedy algorithm from the last section really was very generic. For most optimization problems, you can define some version of a greedy method to find a solution. And it was not nothing. It was a log n approximation is not nothing for set cover. In particular, for this problem, this is conjectured to be essentially best possible. But what else could we do with a set cover instance? If you study these counterexamples or these lower bound families that I've shown you for the greedy algorithm, it seems to fail on instances where the costs are really unfair, in the sense that there's some sets that give you a lot, but then have relatively cheap costs so that the optimal solution can pick them. Maybe we should kind of expect something better if the costs are somehow less unrealistic, maybe. If a set is larger, it should be more costly. That's the vague intuition here. I mean, whether you agree with this intuition or not is maybe not so important. A specific way how this last thing could be satisfied is with a size proportional cost, where indeed now the cost of a set is exactly some constant times its size, but because we're comparing against optimum, you might as well say P is 1. So the cost of a set is the number of elements that it contains. That feels like it should be easier to deal with, just because it's less easy to cheat in the optimal solution to pick some very cheap solution that somehow the greedy algorithm can be tricked into not picking. So let's see what we can do. It turns out we need another notion here, which is the notion of frequency. So the frequency of an element of the universe is just the number of sets that it occurs in. So a very natural thing to look at. And we'll keep this maximal frequency f without any subscript. That's just the largest number of sets that any specific element occurs in. We've seen this before, just I didn't give it a name there. The vertex cover instances are precisely the set cover instances where f is 2, when the element occurs in just 2 sets. Now it turns out if your costs are size proportional, something cute happens. If you take all of your sets, that's already an F approximation. So it's the most boring of algorithms. You just take the trivial solution of picking all sets in the input. And by the magic of size proportionality, you can bound the cost by F times the optimum. How does that work? That's a very simple calculation, as you can see. So it's a one-line proof. You take the cost of all the sets, which is just the sum of all their cost. Now, we know this is size proportional, so each of them is P times their size. And now we're just rewriting the sum of the sizes of all the elements in terms of frequency. If I sum this over the elements, then I get every element exactly Fe times. And F was an upper bound for all the Fe's. So that's basically it, because the optimum solution has to pay at least, or has to cost at least p times n, because it has to pick somehow all the elements. And the most cost-efficient way to do that is to have each element covered just once, and then you would have to pay p times n, because we know so precisely what the cost of sets are. So it's a very, very simple observation, which by itself is maybe not super strong, because first of all, the algorithm is super boring, and it seems that maybe this is too restrictive now. Requiring that an input has a size proportional cost function is maybe overshooting a bit. But we can still turn this into an algorithm by just forcing the cost to be size proportional. And the idea here is what's then called a layering algorithm. We basically pick the smallest proportionality constant to have a cost that is size proportional. Then we take the sets that have exactly that cost, and for the others we have some residual costs to recurse on. So we split the cost of each set is split into a size proportional part and some remainder. So this is just going to be some p times the size. And this one we don't know much about in general, but we make sure that it's always non-negative by just picking p small enough, picking p as the smallest overall sets. You can always make sure that this is exactly 0 for at least one set and greater or equal 0 for all the sets. If that's all you can do, you're not going to make great progress, but we'll see how we can tie things together at the end in terms of this frequency. So first of all, the algorithm in more structured ways, it finds p as the smallest such ratio, so the smallest proportionality constant for any size proportional cost. Then we set z0 as I just sketched here, that's the size proportional part, and c1 is the remainder. And then we just pick for our solution all the sets where this residue part is exactly 0. So all the sets that have the exact size proportional cost, these we pick in our solution for good. So the algorithm is, again, has a greedy flavor, but it works a bit more on what greedy means here. Then we still might have to continue. So we look at all the sets, all the elements in the universe that we get from the sets that we just picked, all the elements with the size proportional part. If that happens to be all elements, we're happy and we just return that solution. And otherwise, we can reduce the instance a bit. We can get rid of all the elements that we've already covered. We don't need to pay for those again. And we can reduce our attention to all the sets that, well, have any elements left in this remaining set. I think we can also remove all the elements that we've already covered, but these by definition fall out of this because U is the universe of all the elements that are completely, so all the sets that we pick are completely covered, completely contained in U, and so they can't have an intersection outside of U with S. So these are all the remaining sets that are still interesting. And then we recursively compute a solution for this problem. But importantly here, we only put the residual costs in. So the size proportional part is already subtracted and dealt with. And we only look at the remaining part. And this is important, otherwise we may not make progress, right? And then the output is just the union of these sets. So maybe slightly less obvious, but if you come from this size proportional idea, this algorithm is somewhat natural. But how well does this work? Turns out you can show it's an F approximation for F, again, this maximal frequency. And you say, hey, hold on, we already have an F approximation. There it is. But that's only if the input was exactly size proportional. Okay, so that's very, very restricted, but we'll use that special case for dealing with the induction basis. The proof is by induction over the recursive calls. That shouldn't be surprising. And we have to show two things, namely that the algorithm even computes a valid set cover. I think from the code, maybe that's not even 100% obvious. And we should show that the cost is at most f times the optimum cost. For the induction basis, we're assuming that we hit the return here in line 8 and then stop, which means all of u is covered by the size proportional part. And well, we've explicitly checked that we are a set cover, so that the correctness part A is fine. And for part B, we invoke the previous lemma, because now it is indeed a size proportional instance if you restrict it to the sets that we picked. So there might be other sets that are more costly, but they're not needed to cover the universe anyway, so you might as well ignore them. And on the restricted instance, where this curly s, I don't know if I can draw a curly s. This is just all the elements that we picked, so the curly z0. This is size proportional by definition, and so the lemma must apply and give us an f approximation. That's the inductive basis. If we return here, what's left is the inductive step where we have to keep going. Now we use the induction hypothesis on the recursive call. So we can assume that C1, where we get back here, covers the universe that we recurse on with the cost that we recurse on. So we only get that the cost with respect to C1 of this returned cover is at most f times whatever is the optimum for this weird recursive subinstance. So we have to work a bit to put that together. Let's suppose we have some optimal set cover with respect to the original problem. So this is our actual target for opt that we fight against. That's giving us this one. So maybe just to make it clear, this is opt. So observe that all the elements that we pick in C0, they have this cost C1 equal to 0. And the elements here, I mean, what we leave here is we can force to apply the lemma by making everything size proportional by just looking at Z0, the size proportional part of the cost. So if I take what I pick and the recursively returned set cover, then with respect to Z0, that's an F approximation because that's forced to be size proportional. So I can remember this for later, that with respect to the Z0 cost, our produced solution here at the end is at most F times the optimal solution, but evaluated with the size proportional cost only. Okay, that's also easy. Now for the interesting part, we have to work a little harder. So first of all, we look at all the elements in the optimal solution, where the set is in the recursive call. S1 was the sets that are not completely covered by the size proportional part. We gotta have that this restriction is a set cover for U1 because all the elements, all the sets that are where this I is in the optimal solution, but not in C star 1, they only cover the size proportional part, so they can only cover U0. And so U1 was the complement, that's what's left. To cover these, I have to use the sets that are in with indices in this curly C star 1. All right, which means that the cost I pay on this set C1 that I pick, that's by inductive hypothesis the optimal solution on this subproblem. And this C1 star is some specific solution there. So the optimal solution must be cannot be worse than this specific solution. This is part of an optimal solution for the entire problem, but for the restriction on the universe U1, it may not be optimal anymore. And sorry, the F is missing here. All we get from the inductive hypothesis is that we get an F approximation, not the optimal solution here. So the F comes from the inductive hypothesis. The second part, the C1 star, this is some specific set cover, and so it's not cheaper than the optimal solution for that set cover. So how can I, yeah. Just for clarity, it's supposed to be a curly S. No. Never use curly letters. It's always a pain. That's U1. Commas and ones also look the same. Maybe I should write them like this. So that's C1 of the curly C star 1. That's what we're using here. And the F is coming from there. But so also remember this part. If I take the part of the solution I get recursively and evaluate it under the residue cost, C1, that's at most F of what I get for the cost of the part of the optimal solution on this universe U1. And now we're essentially ready to puzzle everything together. The cost of our solution that we compute in terms of the actual cost we care about, C, can be split into the size proportional part and the residue part. So far, so easy. Then on the residue part, we know that all the size proportional sets have residue cost 0. So here, this C1 of this set is a sum, and I'm leaving out all the terms that are just 0. And now I'm using my two equations. Let me just copy this one. So we have it on the same slide. So that's what we use here. Each of these parts is now bounded by F times the respective part of the optimal solution. Here it's the entire optimal solution. Here it's just the part on U1, as we defined up here. But again, if I include the sets that are from the size proportional parts, the residue cost is 0. So I can include them. They contribute nothing to this sum. And so I can go from here to here, and I'm not actually, maybe this is even equal, but certainly I can upper bound it by just including more elements here. That's enough, doesn't even need an argument. And then we have just rewritten the cost of the optimal solution. So that is opt. So the overall result is the cost of the solution we produce is at most F times the optimal solution. So the layering algorithm is an F approximation. And note that for vertex cover, we had F equals 2 always. So we get a 2 approximation. Yay, we've already had a 2 approximation for vertex cover. But notice here, this is the weighted version. And so it is a stronger result. You cannot easily get this with the matching argument that we've used last time. Okay, and of course, it also works for the general set cover problem. if f is larger, the approximation rate is not as good, but it's going to be better for all instances where the maximal frequency is below this hn. And well, that's a question that depends on the specific application, but I think it's more realistic to assume that specific elements don't occur a lot of times in different sets. So probably the layering algorithm is usually a stronger approximation. Shall we do break now? It's roughly middle of the time, so even though it's kind of continuing from set cover. use the time to prepare a figure, so I can make it magically appear when we get to the point. In the next section, we'll see an application of set cover to solve a different problem. And because we have approximation algorithms for set cover, we can then apply those to the new problem. So it is if you like, a way of a reduction. The point of this section is to show that set cover can indeed be used as a versatile problem to embed other kind of applications. And the application we're looking at is the shortest superstring problem. Sounds like you're looking for some exciting word, but superstring is taken in a bit more literal form. We have some strings over an alphabet sigma, denoted here by this set of words, W1 to Wn. And we're looking for a superstring, which is some long string that contains every string from this set as a substring. So for every Wi, there's some range, starting position, I don't know, Ji up to Ji plus the length of Wi. And that has to be Wi. That's what I mean by substring. Just to be clear, it's a contiguous occurrence, not a subsequence where the letters can be spaced out. And so, of course, a trivial instance is to just concatenate all the strings one after the other. But the cost is the total length of the superstring. And clearly we want the shortest, so the minimal length. And how can this be shorter? Well, sometimes you can overlap certain strings. And so you can reuse characters to be part of several strings. Without loss of generality, we assume that neither of the words is a substring of another, because then you can just forget about the smaller one. If it was a substring of another, it'll always be covered, so we don't have to take care of it. That's just something that makes one specific argument in a picture a bit nicer. Why is this problem interesting? It's an abstract representation of the DNA assembly problem. If you want to sequence a genome, the original version, how the human reference genome was built, was more like that. You can't actually read such a long sequence of DNA or RNA. What you can do is read short snippets of a couple of hundred characters, whereas the overall thing has billions. So what you do is you read random substrings of the overall string many times. And then it's reasonable to assume that the shortest superstring would be a reasonable way to define what the DNA originally looked like. If you have enough of these samples and they overlap by enough, then there's a hope that that's unique, say. Now, the general problem of finding this shortest superstring, unfortunately, is NP-complete, so you can't exactly solve this. And it's an interesting question how the human reference genome worked around this problem. I suppose that they had additional lab technique tricks, but there's also some ambiguity in the reference genome left, I think. But for us, all that's relevant is this kind of picture of where the problem comes from, so that it sticks better in mind. It's certainly abstracted from this application. So what does that problem have to do with set cover, you may ask yourself? It seems at first not like you could make use of set cover here. But that's what we're going to do. And the trick's going to be to build these kind of pairwise overlaps. And I prepared this picture here. The W, I'm picking two of the strings, Wi and Wj. And now sometimes I can overlap them by a certain number of characters if these are all equal, right? If some suffix of Wi is the same as a prefix of Wj. And this can work for certain lengths, maybe not all, but it may be different lengths. And I'm just taking all combinations of this and call these overall words, so the whole thing from here to here. That's my sigma ijl. I'll be a bit more precise with the length. So okay. That string, that's the sigma ilj. It's also formally defined here, if you prefer that. And of course, yeah, this combination of three numbers is just valid if the overlapping parts match. Now let's define the set of all those strings where the overlap matches. And again, let me stress that we include all possible overlaps, not just the longest. Then we can define a certain set cover instance that is not exactly identical to the shortest superstring problem, but it covers or it represents parts of it, say. I don't want to say something wrong here. The universe is the words that we want to cover. Remember, these are W1 up to Wn. So we're trying to cover all the words with some superstring. And the sets that we're allowed to choose from are the sets as pi, where pi is a word, and it's either one of the original words, I can pick them in isolation, or I can pick one of these pairwise overlap words with any length of an overlap that I want to choose. Now these are sets. So for each string pi, the set is actually all the words that I'm covering in that string. Right, so pi is some string. And I guess if it's exactly one of the words, then there's only going to be this word that's contained in it by assumption. But for the overlap word, I know there's going to be at least wi and wj, but maybe I'm lucky and there's another string that lies somewhere here. So then all these ijk would be in S pi. That's the sets of our instance. So this is just a fancy way of saying occurs as a substring. These I and j have nothing to do with these I and j. Maybe I could have picked a different letter here. So it's just wk occurs as substring. Okay. The cost of such a solution, or well, the cost of a specific set is the length of that string. And the idea will be, if we get a solution from this set cover instance, then we just take as superstring the concatenation of all those strings pi in any order. So you see that we're evading the harder part of the problem, namely that we have to arrange the strings in some specific form. Especially, it's a bit funny if you think about the DNA assembly problem. You would think that the hard part is to figure out in what order you have to put the snippets. And this set cover reduction is essentially saying, I'm not going to worry about this. I'm just deciding what sets I'm going to pick. And then any order is actually equally good. But remember that these pi's are most likely going to be from this set M. And so they contain I and j. So at least these two are put in a specific order. So we're making some progress, but we're, you already see that this is not going to be an exact solution. Maybe somewhat surprisingly, you can show it's a 2 approximation. If you take an instance of the shortest superstring problem, and we construct this corresponding set cover instance with these pairwise overlaps, then you can show that indeed a bit stronger. You can take the set cover optimal cost, and you can sandwich that between the optimal shortest superstring cost and twice that. But in terms of an application, we know that this shortest superstring is NP hard, so we're never going to get this optimal solution here. Well, same is true for set cover, but we've seen some approximation algorithms. So we can get an approximation for the set cover optimum. then use this upper bound to get an approximation for the shortest superstring problem. And for example, if you insert the specific approximation algorithm we've seen before, then you get a 2 times hn approximation for shortest superstring. I'm going to say upfront, this is not the best you can do for this problem. You can study this superstring problem more carefully and get better solutions, better approximations. But the point here is rather to show the versatility of set cover. And I think it's insightful to prove this, because then you understand the reduction much better than from just the definition I've shown you. The first inequality is actually easy to see, because if you take any superstring and you you arrange that, then any set cover solution, if you arrange that, if you build the concatenation of all those pi, that is a valid superstring. And so the best superstring can only be shorter, because this is a specific one. And we've chosen the set cover instance so that within each of these pi's, in total, I have to have every word covered. So that's all that's needed for this left inequality. The interesting part is the second inequality. And so for that, let's assume we have a shortest superstring as star for all those words. And in general, this will not have the structure that we sketched, that there's an overlap only between 2 of the words. In general, this will look different. In particular, I'm going to draw a picture on the next page then. So I'm going to draw it in big on the next page. It's one long string, and it will have certain of the words occur in a certain order. So that's W1, W2, and so on. They all have to occur there somewhere. By how much they overlap, we don't know. We certainly know there can't be a position where I'm not overlapping with any word, because I could just strike out that character. So there will be some order in which these strings occur, and now this is where the assumption from earlier comes in. This one. If no string is a substring of another, that means the order in which they start must be the order in which they end in S star. At least they cannot, I take that back, but they can't be contained within another. So I guess I could have such a case, but the starting point, we'll number them by the starting point. That should be good enough. Okay, to further analyze this, we need to define some groups here. So this is our superstring. And so there's some first word here. And then maybe overlapping that is another word. Maybe it comes a longer one. Maybe shorter, but it always has to reach behind the stopping point of the previous one. Maybe that's enough. Maybe I'll put one more. Okay, this can't exist. It must be overlapping here, and so on. Now observe, I can always say, I'm explaining the definition up here, but in pictures. So there's a first word that starts a new group. That's the word, the index I1. And then there's going to be a number of words that overlap this first word, or specifically the ending indices. And then at some point, I'm entirely behind this first one. So I'm defining a group to end with this overlap here. So the last word that still has something in common with this first one, that's going to be the end point of that first group. And so there could be an arbitrary number of other words in between that I don't know about. Sorry, this is stopping here. You know what? Let's cheat a bit. So the point of this definition, of course, is that if I take the substring of my superstring up to here, that's going to be one of my sigmas. It's, okay, we'll have to give this a name. I think I just called it the previous, so this is I2 minus 1. Fine, so it's going from I1 up to I2 minus 1, and there's some certain overlap. I don't know how long that is. But that's a certain length, so that's my L here. So I can describe some part of this superstring as a sigma ijl. Okay, great. I can, of course, do this with the next group as well. And I can keep going on like this. So this one ends here, and then we have this overlap up to there. It's a long guy. This one starts a new group. And this one's a group of its own. It's probably useful to have a little space here. I'm just going to sketch this guy here. Now, the key observation is that these light blue guys overlap. And so they're not going to correspond to my set cover instance, because in the set cover instance, I'm just taking the concatenation of these pi's. So it looks like we're screwed, but we're not entirely screwed, because it can't be that the light blue guys overlap between one group and two further groups. If I go to the next group, I might have an overlap because there's this blue part here that's sticking into the next red word. But then when this group ends, that means the starting point here has to be behind the endpoint there. Otherwise, this would still be part of the group. So, or say it again, the starting point here has to be behind the endpoint there. So there's going to be some continuation until here. So the starting point here, the endpoint here, has to be behind that endpoint. I don't know. So there's a gap between these two. The endpoint here is behind that guy, which means the starting point of this last guy has to be here. And if you look at group 3, it cannot start before this endpoint, otherwise it wouldn't start a new group. And that endpoint cannot be before this endpoint, otherwise we would have included it. So otherwise this would be contained in that string. That's our assumption. So if I go from group 1 to group 3, the light blue guys cannot touch. They cannot overlap. They can touch, but they cannot overlap. Okay, keep that picture in mind because it's going to go away. So group J starts at this and ends at this. That's what I've just drawn. And we can define these light blue overlap strings. The groups can overlap, so their concatenation might be longer than the superstring. But whenever I jump to the next, after the next group, I get that they don't overlap. Which means if I do take my light blue guys and I'm concatenating them all, I'm gonna at most cover these optimal superstring twice, right? Once with the odd and once with the even pi's. And so that's why the total length is most twice the optimal one. So in a way, the set cover approximation here is useful in that it's only a factor 2 away. The tricky bit is to get a good solution for set cover, which is itself hard to approximate with a good factor. But it certainly can model this problem to a reasonable degree. And as I mentioned, you can do better if you study this problem and exploit its specific properties more. Okay. There's one more really cool thing to cover, and a cool algorithm, and a short remark. I wish I would have swapped the sections. What we might do though, let me cheat here and swap the order. Doesn't matter. This is going to be very short, but I want to use this in the tutorials. Okay, so the numbering will be messed up. Let's do a very brief excursion to the last subsection, just so that we for sure cover this bit. We've talked about randomized algorithms, and we've been talking a bit about approximations, and we will talk a bit about approximations more. But you can also combine the two ideas. And I just want to show the appropriate definitions so that these are clear. And there's two notions that can make sense: a randomized approximation and an expected approximation. So we have an optimization problem. Here I'm assuming it's a maximization problem. And we have some approximation ratio, delta, that we try to achieve. And then we call a randomized algorithm a randomized delta approximation for the problem. If it always outputs a feasible solution, so that has to be with probability 1. And with at least probability 1/2, the solution that it does output has approximation ratio at most delta. So it can output worse solutions occasionally. It can never output infeasible solutions that are not even a valid solution. But it has to output one that satisfies the approximation guarantee at least half the time. So you can already imagine you can repeat this and boost this probability, and you just always pick the best solution that you've seen. The other notion is where we have an expectation smuggled in. So same setup. Now an algorithm is a randomized delta expected approximation. If again, it always outputs a feasible solution, and the expected value of the approximation ratio is delta. Of course, you can define the same thing for minimization problems. It's just that you have to flip these inequalities. I didn't want to have too many case distinctions. I think you can deal with that. Yeah. So these are two different notions that you can partially also convert between. But just so that if you see these terms, you know what's meant. And now we're going back to where we left off. A million clicks later. In the next section, we'll look at some even more ambitious approximation algorithms where you can wish for a specific approximation guarantee up front. These are called approximation schemes. And indeed, for the problems that we've seen so far, these are unlikely to exist. Both for vertex cover and for set cover, as a generalization, we've seen that there are certain barriers below which, so a certain approximation factor, like 2 for vertex cover, where it seems unlikely that we can find a polytime algorithm that beats this approximation factor. For other problems, maybe we can hope for something better. And the appropriate definition is this one. There's two versions of this, p-tas, f-p-tas. You'll see the difference in the running time in a second. So the setup is we have an optimization problem. And here I picked a minimization problem for God knows why. It doesn't matter. So here we minimize things, then approximation ratios will be above 1, right? Because the solution we get is worse than optimum, so it's going to have larger cost than the optimum cost. And an algorithm now is a polynomial time approximation scheme, or p-tas. If it takes two inputs, a number epsilon, small rational number, and a specific instance. And we usually write this with epsilon in the subscript because you can treat kind of currying epsilon in and leaving x. So you get an algorithm where you just specify epsilon. So for a p-tas, this a epsilon has to be a 1 plus epsilon approximation algorithm for you. And it should be polytime, but you treat epsilon as fixed. So the running time has to be polynomially bounded by the length of the input as usual, but epsilon is treated as a constant. And so you could in principle have a running time like this, or I guess even like, yeah, it looks like an FPT time, but nobody forbids us to have something like 1 over epsilon in the exponent of n, or something even crazier than this. Like, you treat epsilon like a constant. I think this should be xp running time if we want to make the connection precise. So you can get an arbitrarily good approximation, but if you view it as a function of epsilon, the behavior, the growth when epsilon goes to 0, the growth could be arbitrarily bad. And so, well, whatever that means, right? It depends on the actual functions. The stronger notion is an f-p-tas, a fully polynomial approximation scheme. It's the same setup, but now the running time has to be a polynomial in both the input size and 1 over epsilon. So if here you view the function that maps epsilon to the running time, I guess I can write this as time a epsilon of n, then now we have another parameter in again for some specific constants. Does that make sense? Well, this function in the p-tas case is unbounded, arbitrary, and for f-p-tas is polynomial. But formally, you should go by this definition. The running time is a polynomial in the input size and 1 over epsilon. Certainly, f-p-tas is a much stronger notion. Maybe it's too strong, right? Does this even exist for any hard problem? We wouldn't study it if it wasn't the case. It exists for some problems, but we'll see it's only a selected class of really lucky problems that will have an f-p-tas. One example is the knapsack problem. A good old friend from Unit 3 when we talked about pseudo-polynomial algorithms. So because it's a couple of weeks ago, let me remind you about the problem and the notation. So the 0-1 knapsack problem means we only have items that we can either take or not take. The items are just numbered 1 through n, and they have certain weights, w1 to wn, and they have values, v1 to vn. And we have a knapsack of a certain capacity b, which is the weight capacity. I can stuff in items of total weight at most b, and my goal is to maximize the value. So these could be separate in principle. And how could we get an approximation for knapsack? What we care about at the end is the value, so we might try to round the values. And by making them more coarse, granular, maybe we can reduce the size of numbers that are involved. And that's how it will tie back to the pseudo-polynomial algorithms we've seen before. There's a slight nitpick or a slight twist, if you want, that we have to get around first. As you all will remember readily, in Unit 3, we solved the knapsack problem with a dynamic program that has this table where we have entries for a prefix of the items. So we're only allowed to use items 1 up to n prime. And we're restricting the weights potentially further than b. So specifically, this v n prime b prime was this largest value we can get for a selection of items among the first n prime ones, where total weight is at most b prime. And then we could get a recursive description of this. We could fill this. And essentially, the running time is dominated by the size of the table, which is n times b, just the number of combinations for these indices in the table. The total time, because you have to compute with numbers, compute with values, you essentially get a logarithmic dependency on the size of these integers because you have to add them up. But even so here, the logarithm of max int, log of max int is always going to be less than the input size, right? Because you have to write down the numbers. So it's the correct way to say it, but in terms of the pseudo-polynomial algorithms where this max int came from, the real culprit is the b here, because b is a number that we have as part of the input, and that could be exponential in the input size encoding. So this solution from back then was great if the weights are small, but now we're trying to round the values and leave the weights unchanged. So it's a little inconvenient. Luckily, you can take the same core idea of a dynamic program and tweak it so that the size of the table depends on the values and not on the total capacity of the knapsack. It's slightly less efficient in general and is slightly more inconvenient. That's why I didn't present it that way in Unit 3, but you can do it. I'll make the assumption here that all the weights and values are natural numbers. If not, you can scale them with they're assumed to be rational numbers, so you can scale them with the common denominator. That might blow up the numbers, so it's not necessarily without loss of generality, but it's an assumption that we use for getting this approximation algorithm here. So this is kind of important. And we define a different dynamic programming table as follows. We take the smallest weight that we can get, again, from items of a prefix, but now we restrict the value instead. We want value exactly v. It's a bit awkward, maybe from just solving the problem, but it works. In particular, you can write a recurrence for this. So the minimal weight I can get to pick items from this set to have value exactly v, I can, if my next item the last item I'm considering here compared to n prime minus 1, if that one has value less than v, then I can try to include it. That's this solution. So I'm including the weight of this new item. And then from the previous items, I want to pick value exactly v minus the value of this new item. And otherwise, I'm not picking this last item, so I have the same solution as I had previously. If my new item is too valuable, then I can't take it. It's a bit, well, that's by definition. It's not so intuitive. The final solution here is more complicated, right? You have to go through, starting at the largest value, you have to go through all the entries and check what's the largest v where you get an entry that's less than b. But you can do it, and you can fill it recursively like this. There's some initial values left. Because we have this restriction equal v, there will be many entries that are essentially left at 0 or left at a plus infinity, because we can't exactly get value v anyway. But that's not a problem. So that's a nice exercise in dynamic programming. But the point here is that we can get a solution, an exact solution for the 0-1 knapsack problem with a total time like this. That comes from the number of entries. We have n for this. And how large do we have to pick the values? Well, at most n times the largest value for any item. And so that gives you that time. It's the size of the table, and then again, computing with numbers takes logarithmic bit complexity. And with that, we can build an FP-test as follows. We make a convenience assumption here that we only consider items that fit in the knapsack by themselves. If they don't, you just remove them, right? They're never going to be useful. This is just something, again, that pops up in the proof, makes arguments cleaner. The algorithm then is conceptually round the values and call the dynamic programming algorithm, because the dynamic programming algorithm is in the running time and space very sensitive to the maximal value of any item. That's going to be reducing the running time. And what we'll have to show is how good this is. But what do we mean by rounding? Specifically, we take k to be essentially the largest value, and then multiply by epsilon divided n. And epsilon is the parameter that we want as an approximation guarantee in the end. So the output is supposed to be a 1 plus epsilon approximation. That's the goal. So we pick a granularity k, defined like this, and we round all the values to multiples of k. Well, I could have included the k here, but we're just rounding them in units k. Or we express all the values with unit k. Okay. And to show that this is indeed an FP test, let's briefly look at the running time. If you look at this code, it's not doing much, so the running time will come from this dynamic program. And you could just plug in what we know here. Let's define this capital V tilde again as the maximum of the VI tilde. So the V tilde is the rounded V, right? So this one is the rounded maximal V. That guy we can bound by the input size, as I mentioned before. It's the log max int. And then we insert what we know for V just by definition. It's going to be the largest V divided by K. The rounding we just ignore, we're upper bounded by that. And then we insert what we know about K. And K will give us another factor n here, up here. It will cancel with the V, and we get a 1 over epsilon. And that indeed is a polynomial in the input size, the size of the encoding of the input, and 1 over epsilon. So the running time is fine. It's going to go up with epsilon, and the space is going to go up with epsilon, but only polynomially. So good enough for an FP test, and probably the best you can ever hope for. We still have to show that this is an approximation. So what I said earlier, I guess, here is a maximization problem. So we want to show that the value of the selection we get from this algorithm is not too far away from what the optimum gets, precisely a 1 minus epsilon factor at most. And that's again a relatively simple argument, but a cute little trick to calculate. We start with an optimal solution for the original problem. By definition, so the value, I'm just going to write v of a set of items to mean the sum of the values. And that's the optimal value by definition. And now if you go, let me maybe copy the algorithm just that we have this on the side. For this, see why this is true, you just have to insert what the v tilde is. If we multiply v tilde by k, then I'm basically scaling up with this k again. And then I have what's written here is k times this rounding down. I can upper bound that by vi. By the way, this notation here is kind of vectorized, like NumPy or MATLAB, where this is a vector v, and you're applying this operation to the entire vector element-wise. So we're doing it for each vi. The upper bound is obvious from this, and the lower bound is kind of also obvious. All you're using is that x rounded down is less or equal x, and at least x minus 1. Okay. Now we use that the dp knapsack returns the optimal solution, but for the rounded values. So what we output will be at least as good as the optimal solution if we substitute the rounded values, right? Because it's optimal for this instance. And also opt, whatever it is, will be at least as big as the most valuable items, because we assume that they all fit in the knapsack. And with that preparation, we can easily puzzle the result together. The value of our selection is the sum of all these values that we pick. Now we're using this inequality from the way here inwards. So it's k times the rounded values at most, so it's at least k times the rounded values. Then we're using that inequality to get from our solution to the optimal. That's this one. Now I'm using this again, but in the second direction. So this is at most on the unrounded values on the same instance, minus a small correction because I'm ignoring the rounding. That's exactly the optimal value. And here I'm inserting the definition of k again. If you already forgot, here it is. And that's epsilon times v. And so now with this last equation, this v is at most opt, so we get our desired bound. In a way, conceptually, this is, I think, easier than the exact analysis makes it seem. If you have a pseudo-polynomial algorithm where you essentially pay this non-polynomial part in the running time for certain numbers, rounding the numbers to something more less precise is going to improve the running time, and you can often puzzle this together to an approximation scheme that way. Because we're out of time, I'm not going to prove this part. I'm just going to make the statement. The proof is not hard. It's a kind of almost an exercise level problem, but I think the connection is really nice to make. You can say having an FP-TAS restricts the problem a lot, or you can say there's deep connections to previous areas we looked at. If a problem has an FP-TAS, so I'm using the complexity theory class notation here, but this just means U has an FP-TAS, then the canonical parameterization of this optimization problem, FPT world, is back. Then that has an FPT algorithm. So for certain problems, this already rules out that we have an FP-TAS. just because we know the problem is W1 hard, at least it makes it very unlikely to have an FP test. And the second statement is a bit of the other direction of what we've just used. If we have an FP test and also the cost of any specific feasible solution is bounded by a polynomial of the maximum value. So this is not a strict, like this is potentially exponential in the input size, and then you take a polynomial of that thing. That's not a strong restriction, but you need it for technical reasons. Basically, if you have an FP test, you can construct a pseudo-polynomial algorithm out of it most of the times. And so it shows that these two notions are really deeply connected. FP test in the sense of rounding and pseudo-polynomial in the sense of analyzing the running time dependency on how big numbers are. They're, with a little bit of closing eyes, the same thing. Okay, let's close that here. And we have one little nugget of an approximation algorithm for next week. And then a little bit of LP fun. You've seen the announcement about oral exams. So I clarified a bit, or got me educated. If you're registered for the exam in the first period, we should try to do the exam in the first examination period, because the reasoning is if people fail and need a second attempt, then they can still register for a second attempt in the same term break. And that makes a lot of sense. Outside of that, if you're kind of reasonably confident that you don't need it or you don't care, then it's not a big deal to shift the examination around. As long as it's in this semester, there's no formal problems. But I'll try to offer some dates in the first examination period. And because people are traveling or holidaying, it means the last week of classes is the most likely. If you wanted to get it over with soon, then the last week of classes, Thursday, seems the best option. Otherwise, it'll be a bit later in the term break. Okay.